Hi, everyone. My name is Ellie. Thanks for coming. I'm an iOS engineer at Uber. In this talk, I'll be going over various aspects of the binary size of apps written in Swift. So Swift has recently become very popular compared to Objective-C. It's more readable, it's more concise, there's less code to write, and it has enhanced type safety, generics, namespaces, type inferencing, closures, a REPL, et cetera, et cetera. But what's the catch? It's still an immature language, so the implementation is less stable, and the optimization is less developed compared to more established languages. It also has a slow build time due to type inferencing, global operator overloading, which leads to complex searches, and complex expression solving. Also, depending on the number of modules and module sizes and their dependencies, it can compile the same files multiple times, even using the latest batch mode in Xcode 10. It also increases binary size a lot. The main topic I'll be covering today is the binary size increase. So why should we care? What's the impact of a large binary size? It takes longer to download. And if it goes over the OTA limit, you need Wi-Fi. And if Wi-Fi is required, some people might not download the app at all. Fewer downloads and bad first-time user experience can directly impact your revenue. For Uber, this was critical because the first-time users download the app, they're usually already on the street, where they're about to request a ride, but there's no Wi-Fi access. As you can imagine, this can lead to a terrible user experience. Large apps also take up more storage space. So if you have limited space on your phone, then you might be reluctant to download the app. It can also slow down the app startup time, because now more content needs to be loaded and initialized to start the app. And also, that requires more memory. If your device is low in memory, it can cause the app to be terminated. It also limits the amount of code you can add. So if you want to do A/B testing or add more features, now there's a limit, and it increases the cost of adding new features. So what causes this size increase? One of the reasons is that the Swift runtime libraries and frameworks are shipped with the app. They're embedded in the app bundle. So if you inspect the frameworks folder inside the app, you will see a bunch of dylibs, such as libswift core dylib, libswift foundation dylib, libswift dispatch dylib, and they take up a lot of space. For example, the libswift core dylib takes up about 60 megabytes, and the foundation one takes up about 9 megabytes. And even after you compress all of them together, it still takes up about 10 megabytes. ABI Stability would allow these frameworks to be part of OS, thus help reduce the binary size. But that got deferred until next year. Another reason for size increase is due to some of the language features. Swift has some nice features, but it comes with overhead, which can lead to size increase. We identified some of these features, and they include generics, large structs, collections, lazy vars, and protocols. Also, if you have overly permissive access control and subclass a lot, then that can also lead to a size increase. At Uber, we rewrote the Writer app in Swift about 2 years ago. We adopted a new architecture and wanted to take advantage of the opportunity provided by a large-scale rewrite to change the implementation language as well. We chose Swift because of the supported features like generics, which we found very useful, and other features that come with a modern language, such as enhanced type safety. But what we didn't realize at the time was the size overhead that comes with by moving to Swift. We had about 1 million lines of code with multiple features and modules. We do a lot of A/B testing, so we had tons of experimental code. We use protocols and generics and other Swift features heavily. So just about 10 months after the rewrite, we reached the OTA limit, which was 100 megabytes at the time. So we started investigating, and here are some of the things we've done. We removed unused code and resources, rewrote extensions into Objective-C, disabled reflection metadata, We analyzed Swift coding patterns, and we built and improved optimization tools and the Swift compiler. I'll go over each one in more detail. But first, I'd like to mention some of the tools we used. We used system programs such as Object Dump, OTool, NM, online tools, and apps for machine code inspection, and Swift Demangler. We use these tools to inspect the binary files to look up the symbol table, the text and data segments, relocation info, and generate machine code. It was important to see what goes into the text segment and data segment because they directly affect the binary size. On the right, you can see how running the OTool command can give you the text segment content and the data segment content. Also, you can run xcrun Swift demangle command to demangle symbols, so it's more readable. As you can see, the text segment contains sets of machine instructions, in this case for a class initializer and function compute. And the data segment on the bottom shows you the initialized data. We also built tools to measure the size per module and the app size per slice in architecture. Apple's limits are on the size of the largest slice in a fat binary, so that's what we focused in as well. We also built a tool to visualize the size trends and analyze the effect of optimizations by displaying what modules or functions were optimized most and showing size changes per function. Now let's dive into each area. First, we removed Deadcode. We do a lot of A/B testing, so we have tons of experimental code. Because some experiments were rolled out more slowly than others, it wasn't always easy to determine which code paths were 100% unused. So we had to spend some time identifying truly unused features in code paths. And we used the analytics a lot to do so. So removing those areas gave about 2% savings. We were being conservative at the time, so the number wasn't as high. But since then, we've added automation to detect stale experiments and also to remove the corresponding unused code paths. So we gained extra savings. We also rewrote our Watch app extension in Objective-C. This was separated and small enough that we could rewrite it easily, and that gave us about 3% savings. We also looked into rewriting the writer app in Objective-C, but because of the size and scalability, this was not plausible. The writer app is much bigger and has a lot more users. We thought about using the Swift and Objective-C hybrid. We first tried this on a sample project to see what the result would look like, but it was risky and the gains were not that high. We had to export some of the Swift types to Objective-C, and that increased the size by about 30%. So the total savings were not that high. Also, it was less type safe because now it introduces all the Objective-C issues, such as nullability and runtime issues. And it can also lead to undefined behavior when mixing Objective-C and Swift objects. So we decided not to proceed with this for the writer app. We then looked into disabling reflection metadata. Reflection metadata is used for dynamic features. It refers to class types, field descriptors, method names, method argument types, and method return types. It's contained in .o files, and you can turn it on or off using the disable reflection metadata compiler flag. We disabled it since we don't use dynamic features in our app. And this gave us pretty large savings, about 7%. We also looked into moving parts of the text segment into the data segment. The text segment is encrypted and then compressed. If you compress something that's encrypted, it doesn't compress well. So moving contents out of the encrypted section can be beneficial to reducing size. We first identified parts of the text segment that can be moved that are not code, but are read-only, so it doesn't get modified during runtime. They include OPSI method names, OPSI method types, OPSI class names, constants, and C strings. We move these to the data segment at link time by renaming sections. With this move, we had to disable Deadcode, because otherwise, when the Deadcode is relinked by Apple, it'll ignore the section renaming we did. And this gave us about 3% savings. We also looked into coding patterns which lead to larger sizes. But first, I should tell you that I'm not saying don't use these patterns. All I'm saying is these patterns come with a size overhead. So when you use them, just be aware of the trade-offs and know what's going on. The patterns that come with the size overhead include use of generics, large structs, standard library APIs like collections, lazy vars, protocols, and use of overly permissive access controls and subclassing. Let's go over each one in more detail. First, generics. Generic functions are specialized, meaning compiler will generate a copy of the function for each type for which the function is used. In this example, function foo takes in an argument t, a type parameter. Function var calls foo with two different instances of type t, which are x model and y model in this case. On the right, we have corresponding machine code. As you can see, compiler generates two copies of the same function, one for x model argument type and one for y model argument type. As you can see, this leads to a code size increase. Next, large structs. Structs are copied around a lot. They are copied per assignment and per function call. If you have a function with a struct argument, all the fields in the struct argument are copied per call at the call site. On the right, we have a large struct called person with lots of fields. On the left, we have several function calls with the same struct argument. As you can see, every time a function is called, the fields inside the struct argument are copied to the argument registers per call at the call site. This leads to size increase. So if you have a large struct, it might be better to use a class instead. Swift standard library APIs, which support both Swift and Objective-C features, are very useful. But it can also increase code size. For example, array in this diagram has an extra layer called the array buffer, which handles both Swift and Objective-C memory management. It decides whether to use a contiguous array, which is a pure Swift array, or an Objective-C NS array, depending on the type of the elements contained in the array. By default, it uses contiguous array if the element type is a value type, and NS array if the element type is a reference type, or an Objective-C compatible type, meaning a type that conforms to an Objective-C, for example. This extra layer and logic lead to a size increase. So if you don't need Objective-C compatibility, it might be better to use contiguous array directly, so it doesn't go through this extra logic. And this can be beneficial to performance as well. Next, lazy vars. It generates a large getter. It first checks to see if the value has been initialized, and if not, it creates one. If the getter is inlined every time it's called, it can lead to a size increase. Also, when you have a complex getter where the initializer call inside the getter can potentially cause a side effect in external variables, it can inhibit compiler optimization because compiler now needs to be more conservative. Use of protocols comes with the boxing and unboxing overhead of an existential container for every type conforming to a protocol. The existential container is a way of representing a value conforming to a protocol in a generic manner. It contains a value buffer, pointers to a value index table, and a protocol index table. The value index table is a table of methods which manage the existential container, such as allocate, copy, destroy, and deallocate. The value buffer contains fields of a value or pointer to a heap buffer containing the value, which conforms to the protocol. It looks up the methods in the protocol index table and performs dynamic dispatch calls. Dynamic dispatch is more expensive than static dispatch because it has a high runtime cost, and it can limit the amount of optimization. If you have overly permissive access control level, such as open or public for your types, members, or functions, this limits the compiler's ability to optimize. In general, make the access control level as restrictive as possible, so the compiler can remove unused code and metadata. Also, if you know you won't be subclassing a class, add a final attribute to tell the compiler this. This helps compiler to optimize because if it's more restricted, it now has more information on how types are used, and it can track what's going on more efficiently. For example, even if a public class is subclassable from outside its defining module, the caller from another module doesn't know that it's subclassed or not subclassed within its module, and that can limit the optimization. But if you add a final attribute, the compiler now knows that that is precisely the type used at the call site, and that can help with optimization, such as devirtualization. As a result of making all these coding pattern changes, we got about 4% savings. Now let's talk about optimization. Usually, a compiler optimizes for speed. In some cases, this can increase the code size, for example, when inlining or loop unrolling. But in other cases, it can reduce size, for example, Deadcode elimination. We wanted to explore which combination of these optimization passes will give us the best balance of size and performance. So we used a technique called simulated annealing to find the optimal order for optimization passes to achieve this balance. This means, given a list of optimization passes that are already enabled in the compiler, search for the most optimal order that results in the most reduced binary size as well as performance. Let's take a look at the Swift compiler flow. It takes the Swift source code and parses it to generate an abstract syntax tree. Then it runs semantic analysis on it and generates a Swift intermediate language representation called the SIL. It applies optimizations on SIL, and then the LLVM IR generation step lowers that SIL code and generates LLVM's intermediate representation called LLVM IR. It then applies further optimization to the IR and generates machine code, which is then stored in .o files. These .o files are then fed to the linker, which will combine all the .o files, optimize further if necessary, and generates the final binary file. Here we have a list of optimization passes. Let's go over some of these passes and see how they optimize codes. Deadcode elimination is self-explanatory and obviously helps reduce code size. Common sub-expression elimination. For example, if you have x equals foo times bar and y equals foo times bar, then the foo times bar sub-expression is calculated once and the result is used multiple times. This generally helps reduce code size. Loop unrolling, on the other hand, often increases the size. This means duplicating the body of a loop multiple times to reduce the loop overhead, such as counter increment, counter test, and a jump. This reduces dependencies between subsequent iterations of the loop, so it can enable better optimization, such as instruction scheduling. But this is intended for performance, so in general, this can increase the binary size. Inlining is where the function call is replaced with the function body, and in general, this can increase the binary size as well. But there are cases where this could reduce the size, such as when the functions are very small, or if the function is called only once, then this can actually reduce the size. For our custom pass order, we reordered these existing passes. There was no new optimization. We repeated and dropped some of the passes to come up with the most optimal order. So what are the actual steps involved in the simulation process? First, we have to determine which modules to run the simulation on. and an initial ordering of optimization passes. Then we built our entire code base several times using this pass sequence and measured the average app size. Then we changed the ordering using guided random search. Then we built the code base with a new sequence several times and measured the average number. Then we changed that ordering using guided random search again. We repeated these steps several times until we found the most optimal ordering. We then saved that to a file and applied that to a compiler flag called external pass pipeline file name. As a result, we got about 6% savings, but it came with some caveats. It's a long process. It took about 2 to 3 weeks at the minimum. And it was risky because it can lead to potential compiler crashes due to reordering. And even though the flag was available, it was still hidden and Apple did not recommend using it. So if they decided to remove it in the future, there was nothing we could do about it. And there was no good documentation for it, so it was hard to find any details about it. Also, we determined the pass order using only a few specific modules as a guide. We try to choose representative modules, but the chosen modules might not accurately reflect the entire code base. And especially if we change anything major in our code base, or if we were to upgrade to a new Swift version, then the ordering might not be truly optimal any longer. So we'll have to run the simulation process all over again. And that's a painful process. So we looked into other ways to do this, and we found Apple's Osize optimization. It wasn't ready at the time, so we tried to see if we could contribute to it. There's already an Osize optimization in LLVM, and this extends that to SID level. The Osize option limits the optimizations that could potentially cause size increase, such as inlining and loop unrolling. Our contribution was fixing the inline threshold handling and introducing the loop unroll threshold. The best results were achieved when combining Osize and whole module optimization. Osize is available since Swift 4.0, and you can check out more at the swift.org link below. This gave us about 6% savings. You can also get extra savings by using the inline threshold or loop unroll threshold flags. And that way you can get about 3% or more extra savings. It also comes with a few caveats. Because some of the functions are no longer inlined, it can have a performance impact. But if you're not writing game apps or apps that require super high performance, this should be negligible. Next, we looked into optimizing protocols. We use protocols heavily in our apps. We have about 6,700 protocols in the Writer app. We use it heavily for a better abstraction and also to enable unit testing. But these protocols come with significant overhead. Compiler allocates an existential container for every type conforming to a protocol at SID level. The compiler overhead includes boxing and unboxing an existential container. The runtime overhead includes the value witness table dynamic dispatch to perform operations on existential containers, such as initializing, copying, and destroying, and the protocol witness table dynamic dispatch to perform the protocol method calls. It's expensive due to a high runtime cost and potential limit on the optimization. It also creates an existential container for every protocol value. It creates it per method call on the protocol instance and per function call with a protocol parameter, even when the value is not used. What does this mean exactly? Let's take a look at an example. Here we have a protocol called myProtocol, which has a function called compute. It takes an argument of myProtocol and returns an int. Then we have a class called argClass, which conforms to myProtocol and returns a hardcoded integer in the compute function. Note that the protocol argument is not used here. Then we have myClass that has a function foo. Inside it, it creates instances of our class x and y, and calls the compute function on x, and passes in y as a function argument. On the right, we have the C code generated by compiler. As you can see, there's an init existential adder call, which creates an existential container, and an open existential adder call, which returns the contents of the instance, where a protocol method is called on. In this case, the instance corresponds to variable x. The copy adder call then copies values stored in the existential container corresponding to variable y onto another stack location to pass in as an argument to the compute method. Finally, it calls the witness method compute. Again, note that all these calls are made even if the method doesn't use the protocol argument at all. This is the full C code for the function foo, showing all additional overhead. Besides the calls we just saw, it also calls alloc stack, dealloc stack, and destroy adder to manage the existential containers. So we worked on removing all the overhead at the compiler. The good news is that it's in the latest Swift master. It's not released yet, but if you install the latest Swift toolchain from the master, you should see this optimization. It's enabled by default, so now you can use these protocols without worrying about all this overhead we just went over. So what are the actual steps involved in the optimization? First, it runs protocol conformance analysis, which finds all the types that conform to a protocol for each protocol. Then, using the data flow analysis, determine which concrete types map to a protocol at a given call site. Then transform a protocol function to a generic function with a protocol constraint, which will be specialized later. This step is called existential container transformation step. After this step comes the concrete type propagator step. By this point, you now know the concrete type in the given context. So now you can replace the protocol type with a concrete type. In the example we just saw, my protocol is now replaced with R class. Next, replace the protocol witness method with a concrete type method. This means removing dynamic dispatch. And this step is known as devirtualization, and it can improve both size and performance. In addition, devirtualization can dramatically improve other optimizations as well by giving more concrete information to the optimizer. Next, the generic function with the protocol constraint from step 3 is now specialized with a concrete type. This phase is known as generic specialization, and this can lead to a size increase, but there's a heuristic which can be modified to limit the size increase. The results have shown improved performance by more than 8% on startup time on iPhone 6s on 6700 protocols. This gave us about 3% savings in size. The number could be higher if you tune the size increase limit during the generic specialization step I just mentioned. As I mentioned before, this optimization is currently in the latest Swift master, and it's enabled by default. And it'll be out in the next Swift release. So putting it all together, we reduced the total size by about 25%. Since then, Apple increased the OTL limit to 150 megabytes, which was a good news for us. We added enforcement such as linter rules to follow binary size efficient coding patterns. We started running the size estimate tool on CI to keep track of the size. And we used the visualization tool to track the size trends. We also wrote automation to detect stale experiments and remove unused code paths. And we also wrote a tool to detect duplicate code. And we also have a specific code review group to enforce better coding patterns and limit a potential size increase. To recap, Swift has some nice features, but it can lead to a size increase if not used carefully. Binary size affects app download, app startup time, storage usage, and memory usage. Most apps are not that big, but you can still apply compiler settings and coding patterns to keep your app performant and size efficient. Also, Swift compiler and toolchain are open source, so they can be modified by the dev community. So if you feel ambitious, maybe you can try this out yourself. So what are the key takeaways? What does this mean for you? The biggest takeaway is use Osize settings and upgrade to the latest Swift compiler. The Osize setting is available in the build settings. By default, it's set to -O for the release build, but you can change that to Osize. And you can also use the inline threshold and the loop on roll threshold flags to gain extra savings. There's a lot of optimization work that went into Swift 4.2, so if you switch to Xcode 10, you should see a significant drop in the binary size. In addition, keep your code base clean, remove unused code, boilerplate, copy-paste duplicate code, unused resources, and refactor. And restrict access control levels. Use internal or a private, and add the final attribute wherever possible. This way, compiler can optimize code better, and it'll help with code size and performance. And these are good coding practices anyway, so might as well do it. And if the above is not enough, then you can try work around some of the coding patterns we went over, which come with a size overhead, such as generics, structs, lazy vars, etc. Like I said before, don't just blindly use them. Keep in mind that these coding patterns come with trade-offs. For most apps, though, using the Osize settings and the latest Swift compiler version and keeping your code base clean should be sufficient to reduce the app size. That's the end of my talk. Thanks.